So as usual, the muddy points are discussed first from last class. What is the physical significance of a wave number vector? That is not. So what we said is that we are considering that there are these wave fronts. Say this is phi is equal to 0, phi is equal to 2 pi, phi is equal to 4 pi, and so on, that are going across this domain that we are simulating, or that we are solving for. And of course phi is equal to minus 2 pi and so on. So the wave number vector is just the direction of that is orthogonal to these wave fronts. So this is the wave number vector, and the magnitude of the magnitude or the norm of the wave number vector is omega by c naught. So that is what we mean by that is the physical significance of the wave number vector. Is that clear? So the mathematical thing is that we posed the governing the solution as some a e to the power I omega t minus kappa dot x. So that is what we posed, and then it turns out that kappa is related to the physics as such. So moving back to where we were talking about Helmholtz equation. And for a uniformly moving medium. So we started from the equation in the physical time domain. So we had this d0 to d0 t square p prime minus c naught square grad square p prime is equal to 0. So this was our physical problem where d0 encapsulates the motion of the medium. And so we saw that with this Galilean transformation, that is defining x star equal to x minus u0t, that is we have hopped onto the moving medium and time remains as it is. So we could transform this equation to del t star to p prime minus c naught square del star to p prime equal to 0. So this was the transformation that gave us a form that is now very intimately familiar to us. So we can do a Helmholtz form of this. So the Helmholtz form of this will be omega star, or we don't even need to go there. We will just write the solution for a particular frequency. So we can now say that p prime at an x star and t star, from our knowledge of the solution for the xt problem, is e to the power I omega star, which we are yet to find out, t star, which is our change time, kappa star, which we are yet to find out, and x star, which is our moving position coordinate. So this is what we know from our solution for the quiescent medium problem, where it was everything without the stars. So then, recalling that this x star is x minus u naught t, we can substitute that. And t is just t star. So minus kappa star dot x minus u naught t. So then I can grab the time terms together. Omega star plus kappa star dot u0 t minus kappa star dot x. So comparing with our expected solution for a plane wave, so recall for plane wave in a quiescent medium, but the medium doesn't matter, the solution is what we are looking at. We found that Pxt is equal to A e to the power I kappa, sorry, omega t minus kappa dot x. So comparing these two, we can say that kappa star is just kappa, right? So just compare these two. So in the lab frame, that is in the xt frame, the wave number vector appears the same. Okay? There is no change in the wave number vector because of the motion of the medium, but your omega is omega star plus kappa star dot u naught. So recall that omega star is the frequency of the source. Right? There was some source or some, yeah, this is a source that is continuously on. That's why it is sending out this harmonic wave. It's not a single pulse like this Gaussian pulse that you are solving for. It's not that. It's a continuously going on source with a frequency omega star. That's why we have this solution. And so that omega star is something. Omega is what? Physically, I am sitting here. I am an observer. It is the rate at which wave fronts are going past me. Frequency corresponding to that, right? That is what I have defined as omega. That is what we made sense of this omega. So that is related to this omega star, but it has got an additional kappa star, which is kappa. So going back to that picture, that was the response to that question. So this physical picture, in if you take a snapshot, this remains the same. Kappa star doesn't change. So whatever was the wave number of the source, that remains the wave number that you will observe by an observer that is stationary with the moving medium or not. But in time there is a change. So if we now put things together, you will recall that as part of the solution, we also found that kappa star was omega star by C naught. Remember, that was a dispersion relation. So that has to be satisfied between kappa and star and omega star for this to be a solution of our Helmholtz equation or the wave equation. So this kappa is kappa star, and so I can say there is a kappa hat dot u naught times the kappa star. So this kappa is a vector. So I'm writing that as the magnitude of the kappa vector, kappa star, times the unit vector along that kappa division. It's just a fancy way of writing that. So omega star. So this kappa star dot u naught, I'll just go back to that picture. So suppose now that on the same picture, that is your u0, that is your u0 vector, that is the motion of this medium. So then it is the dot product between these two, the kappa star and the u0, that we are asked to take, right? So it will be the magnitude times the angle between these two, which is some phi, or do I use phi? Theta, no, phi is what I use. So then the kappa star dot u0 will be the magnitude of kappa star, which is denoted by kappa star, times the magnitude of u0, which I'm going to denote as u0, times cos phi, where phi is the angle between these two vectors. So again, u0 is the magnitude of u0. Okay, thank you. I'll use theta. The notes have got theta, but so what? So going back and plugging that in here. So this is kappa dot u naught is kappa. So this is kappa star, the magnitude, u0, the magnitude, times cos phi. But that kappa star is, by the dispersion relation, omega star by C naught, u0 cos phi, and u0 by C0 of course is the Mach number associated with the base flow. So m0 is defined as the Mach number of the base flow. So this is omega star 1 plus m0 cos phi. So that is our omega. So the observed frequency, remember that frequency is related to omega by 2 pi f. So the observed frequency, you are sitting here and counting, stopwatch counting when the wave fronts pass by. And so what you measure is different from what the wave frequency was sent out by the source because of the motion of the medium. So the medium is hastening things if phi is within minus pi by 2 to plus pi by 2, because these waves are aligned. So this, whenever theta is between plus minus pi by 2, so this wave front propagation direction and the base flow direction, they are aligned, at least partially aligned, and so there is a hastening of the motion. When they are anti aligned, then there is a reduction. So that is obvious from this theta in my equation. Everywhere is theta based on the Abhinav correction. Okay, but the kappa star remains the kappa. So this is what is the result of this moving medium. Now, as I mentioned at the beginning, the question was, is this Doppler shift or not? You know about Doppler shift. Is this Doppler shift? Frequency is indeed changing, but in Doppler shift, what you see very commonly are these wave fronts which are piling up. So this should be a very familiar picture to you, where and we'll also solve this problem explicitly. So these are the wave fronts that were sent out at earlier and earlier times, and they are piling up. We can see that pile up here. So the wave number vector will be changing because of the motion of the source. This is motion of the medium. So they are fundamentally different things, and so we should not confuse them. It does look somewhat like that. Physics are different. So we will look at the Doppler shift also. Okay. This problem did not explicitly consider the source, right? We didn't ever consider the source. We just thought of as some waves having been let go into this medium. What do you think the source is doing in this case? If there was a source, what do you think it will be? We'll talk about that actually in a few minutes, okay? And it will probably be a bit more clear about what the source might be doing in this case. Okay, my contention is that the source is static, so we'll see why I want to claim that. So one last point is about the phase speed. So phase speed we discussed for quiescent medium. We saw that Cp is just C0. For a moving medium, how do you define the phase speed? How did we define, what was the elementary definition of the phase speed? Limit, yes. So it was a limit delta t tending to 0, delta x by delta t, where that delta x is a very special delta x. It was normal to the wave front. So if you do that exercise, you will find out that this is the appropriate form of that for our problem. Omega star by k star, kappa star. Omega star by kappa star, of course, my bad. Yeah, omega by kappa, right? And so that we just found out is omega star into 1 plus m0 cos theta by kappa star is omega star by c naught, and so this becomes c naught into 1 plus m0 cos phi. So going back to the picture, this wave front is not moving with c naught speed. What is this motion's velocity? C naught along with the... Yes, so it's a vector sum of these two. C naught in the direction of motion, that is the meaning of C naught. The velocity at which the wave front is moving, but that is with respect to the moving medium. But the medium itself is moving at a different angle with some speed u0. So it is a vector sum of C naught and u0, which will give the resultant velocity of that wavefront. And so the speed of that is the magnitude of the velocity. So that comes out to be this thing. And as expected, there is a same looking form as we had before in the omega star for the same reason. So you can figure that out. So the definition of phase speed is perpendicular to the wavefront. If it is again shimmying this way, I don't care. I can't measure, I don't care. That is the tangential motion of the, what is it? It's plane wave. So whatever is happening in the tangential direction doesn't affect me in any sense in the physics. And so we don't care. If you look at that, of course, there's a velocity like that, but that doesn't affect anything. Medium speed is m0, the medium Mach number. That's there. So m0 is u0 by c0. So that is of course there. I mean that's what we are discussing. And so if this was 0, we'll back to c0. This is the lab frame. So CP is in the lab frame. So everything is inertial here because the moving medium is also inertial, but this is in the lab frame. So that lab frame actually answers your source question. So we'll talk about that in a moment. Okay, so till now we have been discussing about propagation of acoustic waves. We talked about propagation in quiescent medium for a Cartesian 1D wave, for a spherically symmetric wave. Then we started looking at this moving medium. We got some elementary insight into that. There is a whole very relevant branch of this problem, which is the motion of the propagation of acoustics through a sheared medium, as in jet. So that is my business, so jet noise, and we do that a lot, but we will not be covering that here. So we have got other things to look at. But this was all propagation. So now we'll shift gear and look at what is this thing that is creating this thing. So it is a source.